Good. So good morning. We are continuing the lecture of yesterday, and we are going to discuss. I was discussing, so I remember to you make a small recap what we were doing yesterday. So we introduced the concept of sister algebra. So it's complete norm algebra, which has an involution and which satisfies what is called, the sister condition. Okay, so remember the sister condition essentially is this condition in this particular combination. This particular combination has norm equal to a square. Okay, so this is sister condition. And then, so we choose this as our model, our space, our algebra, which contain in particular the physical observable, which are the self-adjoint elements, which are the elements which satisfy that. And, sorry a moment. So we had that, and then we introduced the notion of spectrum. So spectrum of an element, okay, which is the set, so lambda belongs to the spectrum. Spectrum is a subset of the complex number, if and only if this particular element in the algebra, sorry, this element in the algebra is not invertible, okay? In A. Okay, let's discuss this. So this is in A. So I was so far I was just using A for the algebra. So remember, A is A will always denote for us. Sorry, this morning I'm not very efficient. A will be a sister algebra. Okay, A is a sister algebra. And then the sister condition is this. Then you have self-adjoint, you have normal operator, which essentially, if you want, you can think to self-adjoint as so are the observable, but essentially are like real numbers. Okay, so let's consider this way: non-commutative real numbers, and then you have normal operators. And normal operators, you have to think to them as non-commutative complex number. Okay. So these are, and any operator can be decomposed in, so if you want, let me remark this just to, please ask question if you feel, I don't want to lose anybody. So it's part which is like more algebraic, more abstract, but somehow I find it interesting because somehow it's where we come from. Okay, we come from a modelization of, abstract modelization of what are the observable, what are the relations between the observable. Okay, that's why we try to understand. We want to assume as few mathematical assumptions as possible. And somehow the self-adjoint element will be for us the observable. Then the normal operators are just somehow complex valued observables. Okay, so any A can be decomposed. So just to understand what I'm saying, so any A can be decomposed as a in real and complex part. Okay, so this is self-adjoint, but okay, but not necessary commuting. Okay, so that's the point. Okay, in general, we are not willing to assume commutation of the elements. That's the main difficulty in this business now. And any element can be decomposed in real complex part, but they would not be commuting. And for normal operator, it's normal. Okay, sorry, the element. So I'm thinking two operator in Hilbert space because at the end of the day, this will be concrete realization of these sister algebras. From a philosophical standpoint, it's better to keep this distinction so far. Okay. The spectrum. So the spectrum somehow is will turn out to be the conceptualization of the possible values the observable could take. Okay. So it's a subset of the complex numbers, and essentially, yeah, somehow the idea is that this is not invertible in the sister algebra. Actually, then you come to realize that if this is not invertible in the sister algebra, then is also not invertible in the algebra generated by in any. So let me write like this. In any subalgebra. I think subalgebra containing A and A star. Oh, no, maybe I don't even need A star. Okay, let me state in this way. Okay, so this is the idea. If you have a subalgebra which still contain A, then somehow non-invertibility in the full algebra is equal to the non-invertibility in this subalgebra. So in particular, you can compute the spectrum with respect particular. We can use the sister algebra generated by, okay, so which we denoted this, okay, to compute the spectrum of an element. Okay, so that's important observation for us. So the spectrum really depends on the algebraic property of the element A, not essentially in which sister algebra is contained. Where this comes from? Well, remember that somehow yesterday we introduced the resolvent, so, and the resolvent, we essentially proved that in the, so this is the resolvent. So the resolvent is analytic in in the complement of the spectrum, and when lambda is very large, I argued that essentially you can define the resolvent by a convergence power series expansion, and you look at the power series expansion, you see that it only depends on A and on powers of A. So the resolvent, it's really contained in the sister algebra, in the sister algebra generated by A. Okay, so that's the intuitive reason. Okay, so let me go on. Then we introduce the idea of linear functional. So remember that I call linear functionals on okay, continuous action on a Banach algebra. So I call B star the continuous linear functional on the Banach algebra B. And what else I introduced? And then I introduced the idea of multiplicative functional. It does not have to be linear, by the way, because then you prove that any multiplicative functional is continuous. Okay? So this is multiplicative functional, can be defined on any algebra. So far, I'm not discussing commutative. Yesterday, actually, was a bit confused myself because somehow I noticed that so multiplicative functional you can define on any algebra. Okay, it's just some linear functional from the algebra to see such that it satisfies multiplicative condition. Okay, and then they are continuous. It is continuous. And we proved that yesterday. We gave an argument for the continuity. You can, and then therefore multiplicative functional belong to the set, the space B star. Okay, remember on B star there are two topology. There is a norm and also and weak star topology. Okay, which is the coarsest topology, makes all the linear functional, all the evaluation continuous on elements of B continuous. Okay, weak star topology. And then introduce multiplicative functional. They are continuous and actually end of norm 1. Okay, that is if for any multiplicative functional, sorry, for any multiplicative functional, the value on the identity is 1, and actually the value on any other element is less than the value of the identity, which is 1. Okay, so the norm of the element is 1. Remember, the norm of linear functional we defined to be in the supremum over all the elements in the algebra of phi of A. Okay, so this is the definition of the norm. So let me put it here. Okay, and we call the space, so the compact space of linear functionals, linear multiplicative. We call it this Gelfand spectrum, okay, of the algebra. So this construction is general, okay, but then you realize that for non-commutative algebras, it's not very interesting because somehow these objects have to be 0 for many, okay? Okay, not that, okay? So if you compute, let me introduce this notation I will use often later, okay? This is the commutator of two elements, that is this, okay? So commutator. Of course, it is non-zero only if the algebra is non-commutative, and then you realize that on any commutator, multiplicative functionals do not get any interesting values because, okay, they give phi A minus phi B, and then on the other part, phi B minus phi A, but this is equal because, of course, you are somehow they are homomorphism to a commutative algebra, so you get 0 here. So they get 0 most of the time, actually, okay? Anytime you can write an element as a commutator of other two elements, then they have to be 0, okay? So this map is not very interesting in that case. So the next thing we want to say are really interesting for non-commutative algebras, okay? And now for commutative algebras, okay? Yeah, let me see what I wanted to say now. So we proved, the last thing we proved yesterday was that the spectrum, anyway, okay, it's a compact, okay, because it's contained in the unit ball, is compact in the weak topology. It's clear that being multiplicative, okay, is a property, okay. If anything, it's a limit, a generalized limit of linear multiplicative functional, then it has to be multiplicative because this relation will pass to the limit, okay, in the weak star topology. And then if, so the spectrum is a compact Hausdorff space, okay, that's interesting. And we can define the Gelfand transform, so remember, and the Gelfand transform of A, that is at A is, so the Gelfand transform is just the function on sigma, on the spectrum of the algebra B, which just is the evaluation of the linear function on A, okay? Is a continuous function on sigma, okay? This is by the weak star topology. Okay, so Gelfand transform so we can send any element on B into a continuous function. So we can send it into a continuous function on sigma B. Okay, so we have this map so far. Good. Now, it's funny to look at this map in specific situations. Okay, so maybe you want to try yourself. Okay, so let me do a remark. So if B, so I told you this is Banach algebra, okay, with the convolution. So let me take this Banach algebra, the convolution, and with the L1 norm, then the Gelfand. So, okay, so let me make another remark. So the Gelfand transform, continuous function, moreover, let's see what happens to the Gelfand. So what is the Gelfand transform of a product? Okay, so this is defined as phi of B, but so we see why we want phi to be multiplicative. Okay, so this does not depend on the multiplicative, but then let's try to look at the Gelfand transform of a product, and it's multiplicative. So this is the product of the two elements, and so this is actually the product of the Gelfand transforms. Okay. So the transform, the Gelfand transform is an algebra morphism. Okay. And moreover, and so let's see what happens to the norm of the element. Okay, so somehow I decided already, so on this space you have natural norm, which is the norm, the supremum norm. Okay, so it's the interesting norm here because you see product go into pointwise product. Okay, so with the supremum norm, what will happen? So what is the norm of an element in, okay, let me say what is a normal an element in this algebra. Of course, I have to decide what norm I take, but if you want here, I take the norm. So this is the definition, taking the sup norm on this space. Okay, we have, so this will be like the supremum over linear functional of size 1. Okay, but that's all the, so essentially we can, let me just write this way. So supremum multiplicative functional of so let's see the product. So this will be the value, okay, on this point, but then I decided that this is just pointwise product, okay, on the algebra, okay. So this is what makes sense in order for this to be a algebra homomorphism. And then, sorry, this is, yeah, this is, sorry, is only absolute value, okay. So here. And of course, so this is less than the product, as you can see. But what is this? Okay, so this is just phi of A times phi more of B. So this is less than phi of A, phi of B. And so this is less than the norm of A, the norm of B. Okay, so you see that what I, okay, sorry. Yeah, here actually I don't want to do this in this way. This is not what I wanted. Of course it's true, but it's not my point. My point here was just to prove that the norm on the, so it's easier. Anyway, I already proved that I can use the sup norm because essentially sup norm satisfy the inequality for the product. But here what I wanted really to prove is only that the norm on this space, so which is this one, sorry. And then this is really just the norm of phi of A, as I stated below, so I don't need all this. And of course, this is less than the norm of A, okay, because you normalize A, then this is of norm 1, so this is the norm of A times the norm of phi, and norm of phi is 1, because we are in the unit mode. Sorry. Okay. So we are in the unit mode, so this is the norm of A. Okay, so it's contractive. Contractive. Okay, so the map the map A hat A is contractive. Okay. And then in this case, so the Gelfand transform, you can try to work out the detail, and maybe it's useful exercise. And then you will realize that the Gelfand transform in this case is, can you guess? Can you guess what is the Gelfand transform in this case? And actually, so the Gelfand transform will be Fourier transform. While for L1 of R plus, okay, is defined above, where the convolution is defined as restriction from there. The transform is the Laplace transform. Maybe one could work out the details. Okay. Okay, this is just a remark. It's not very important for us because somehow these are the cases where so I told you I was not sure. Actually, I doubt that these are sister algebras. Okay, so we are really interested in sister algebras. Before going there, I need some more information about this space. Okay, and you saw that there is the risk that this space is quite small. Okay, I mean, because many linear functional, they just, for structural reason, have to be 0 on many elements, especially if you are not in a commutative algebra, okay? So I need somehow more information that this homomorphism, it's nice, okay? Otherwise, it's not very useful to use this transformation to study the original place in the first place, okay? So we need to ensure that okay, let's say let me write sigma is large enough, okay? Or let me point out differently, I need to be sure that the space, so this map send my initial algebra. Let me say, okay, so this map is sending my initial algebra. So we have, okay, at this point we have this algebra monomorphism, okay? And yeah, okay, so this map is sending my initial algebra into the algebra of continuous function with the subnorm. So something I know very well, and I need to ensure somehow that this homomorphism has some, retains some property of the initial algebra, okay? Send any element to one, it's not very interesting, okay? Looks quite like B. Okay, so this is of course not, okay, but just to explain to you the reason, okay? And in order to ensure this, okay, then I need to require that, we need to require that B is commutative, okay? So this transformation does not work very well with, in order for the transformation to be useful, we require that B is commutative. Okay, so this is the restriction of this approach. Okay, we decided to do this mapping, to use this transformation, and then you realize that in general there are problems to using this transformation because of this phenomenon. And then you think a bit more, and essentially, at least you have to require that it's commutative, and this is all you need to require somehow, because now let's see what are the consequences of requiring that the algebra is commutative. And so now we have to understand something. So I don't want to make it too technical. There is no point in this introductory lecture. I want you to get the feeling of what we are doing, and to see that some of the statements we can prove because somehow are relatively easy and interesting to see how one proves this kind of statements. Other statements, I think they are a bit technical and they a bit out of the scope of the present course. So I will just mention them. You can look into the book for details. And the idea is that so now we have to understand what is the space of multiplicative functionals, okay? And then the point is that for commutative Banach algebras, one can prove that linear multiplicative linear functional corresponds, maybe you even did it in your course of algebra, I surely learned it recently. So multiplicative linear functionals corresponds to maximal proper ideals of the Banach algebra. Okay, so there is a one-to-one, okay? One-to-one. Okay, there is a one-to-one correspondence between multiplicative linear functional. So if you want this theorem, okay. I would not prove it. Okay, so let's just explain what does it mean. It's not difficult, but okay, it requires some work and some notions on the way. So let me, for a commutative Banach algebra, so let me rest it properly. Multiplicative linear function correspond to maximal proper ideals. Okay, so what is the idea? So the idea is that any multiplicative linear functional so if you have if phi of a is 0, okay, imagine you have a a linear functional which send an element to 0, okay, then phi of AB is 0, okay? So the kernel of phi is an ideal of B, okay, meaning that every time you multiply B with any element in the kernel, you stay in the kernel again, okay? That is. Okay. So let me, so please ask question if you're not familiar with the notion, okay? So AB is in the, is in the kernel of phi for any phi in the kernel for any A in the kernel of phi. Okay. So that's by the multiplicative property. Okay, so any multiplicative functional define an ideal of B. On the other hand, if you have so from an ideal in general, from an ideal, one cannot construct, okay, a multiplicative function, okay? But if the ideal is maximal, okay, the maximal ideal of B, it's B itself, okay? So you have to require that it's non-trivial, so you say it's proper, so proper meaning does not contain the at least one element, and you see that there is one element an ideal should not contain, okay, and the element it should not contain is the identity, is the unit, okay? Otherwise, if the unit is in the ideal, any other element is in the ideal, because any other element can be expressed by multiplication with the unit. Okay, so to be maximal is to require that at least does not contain the unit, okay? And that there are no other, for the ideal I to be, but if the ideal I is maximal and proper, then one can show that it is closed in the topology of B. Okay, that's somehow quite natural if you think, because if you take limits, and if you're staying inside the ideal, then also the limit will stay inside the closure of the ideal. Okay, so if an ideal is not closed, then you can take the closure, then you prove it's still an ideal, and then you can contradict the maximality. Okay, so it has to be closed, and somehow when you take the algebra and you quotient out the quotient, so this quotient is just the family of, so it's the algebra made by the equivalence classes modulo element of I, okay? That is, so an element in the quotient, and you can introduce a natural norm on the quotient, okay? Is the equivalence. So let me write in this way. Is so the equivalence class of is just the element plus the ideal, okay? And you can check that this is still a Banach algebra, okay, with the norm induced by the norm of the original space, okay, the distance of this subspace from 0. That the quotient is still a Banach algebra, and that in the quotient the spectrum, all the elements are invertible. Okay, so that's how the proof goes. I don't want to do the detail, but somehow the idea is that you take the quotient. So you try to see what's in B, which is not in the ideal, and then you realize that by the property of I to be a maximal ideal, because I, due to the fact maximality of I. Okay. I'll try to work out. Maybe this is nice exercise. It's not difficult, so you can try to think about it. Think about it, and so all the elements are invertible, and due to this fact, one can prove that actually this quotient, it's very simple. Okay, if all the elements are invertible, then the spectrum is apart zero. All the elements, if you want, apart zero, are invertible. Okay, and due to this fact, you can prove that the spectrum has to be C. Okay, I told you the spectrum cannot be empty of an element, and but essentially, if all the elements are invertible, this is called. Okay, this is quite easy to understand. Okay, remember I told you the spectrum of an element cannot be empty because this is a Banach algebra, but all the elements are invertible. So the only solution to this dilemma is that actually, so one has that this is zero for any, the resolvent, yeah, so the element has to be zero, okay, because for any element different from zero are invertible, or element apart from zero are invertible. Okay, so one has that this has to be zero, and then conclude. Okay, and then this is really just a scalar. Okay, so I think the main thing to understand is maximal ideal. When you quotient via maximal ideal, you get just scalars. And at this point now, it's easy to get a multiplicative functional, okay? So given a maximal ideal, proper ideal, one can construct a multiplicative functional by, because somehow by letting, so phi, letting phi 0 on the, so what I do, I just stipulate that phi is 0 on the full ideal, and phi is 1 on 1. Okay, and that's completely define. Let's completely define the functional, okay, because I proved that B essentially is C plus I, okay. This defines phi on all B because okay, we proved essentially that this is I plus C, okay. So you give the value on C, which is given by this, by the linearity, and then you give the value in I to be 0. Okay, so you have this correspondence, okay, which is quite natural. Okay, to have an understanding. So commutative Banach algebra is, we saw the algebra of function on a space. Okay, so think about this relation when you think of a space. So what are multiplicative functionals? Essentially multiplicative functionals in that case. So okay, let me yeah, so let's take an example. So yeah, let's take an example just to make things a bit clearer, less formal. So we take the Banach algebra given by the function on some space. Okay, now let's say function on some space. Okay, and then what are multiplicative functionals? Okay, and okay, maybe it's still not obvious from the discussion so far, but essentially multiplicative multiplicative functionals are just Dirac distribution in given point, any x in x, okay, and ideals and maximal are the maximal proper ideals so they have to correct. So any multiplicative functional is just a delta function in a given point, and maximal proper ideals are always of this form. So is the space of functions such that f of x, okay, is equal to 0. So a continuous function which has value 0 in a given point. Okay, then you check that this is an ideal. Cannot be a larger ideal, and all the algebra is just made by constant, and this ideal, of course, okay, because the only thing you have to do is just to get a general function is just to get away from this condition, and then you have to construct the multiplicative functionals and on this ideal, and this is closed, and this is maximal. And then the multiplicative functionals, so they are 0 on this function, and they take value 1, and so they are the delta functions. Okay. Okay. And if phi is yeah, okay. So phi, let's say phi corresponds to the ideal. Okay, let's think about it. Okay, seems quite easy to me. Okay, but this is interesting example. Okay, so if you have problem just to get the feeling of what I was doing here, maybe think again having this example in mind. Okay. Good, and actually this is all we have. Okay, so this is all we have to do now. Okay, we have this very nice structured theory for multiplicative functional in commutative Banach algebras, and then I can prove, let's say, of all this construction. So from now on, so assume B is commutative, then I can prove that if A is invertible, okay, let me not state the theorem first. Okay, let me understand what I'm going to do. Okay, so now take a commutative, let's say, call me abelian. Okay, so abelian and commutative just the same. Okay, abelian Banach algebra. And let A be an invertible element. Okay, so there exists its inverse. Okay, therefore we know that 1, so and phi multiplicative. Okay, so let's take phi multiplicative element. So you have 1, it's equal to that, but that this is phi of A and phi on the inverse of A, and then this means that the function A and the function, so let me write in this way, and the Gelfand transform of the inverse, this is 1, okay? It means, okay, so what does it mean? It means, therefore, this element in the, therefore, this is invertible in C of sigma B, okay? And the other way around, okay? And this is, okay, and the other way around. Okay, so invertible elements, okay, if I it's invertible, sorry, let me say, so this is invertible. Okay, so if I it's invertible, this is invertible. So what does it mean? This implies that, so recall, okay, so this is the set of value for which lambda minus a hat. And so this is, so now I'm taking the understanding that when I'm working with a hat, I'm in this algebra. When I'm working with the elements, I'm in B. Okay, so this is the spectrum really on this algebra, okay, of this element. So this is the set of complex number for which lambda minus a hat is not invertible, but this corresponds by this reasoning to the same set of elements on the other side. Okay, so this is really equal to the spectrum of A in sigma B. Okay. And I can compute the spectrum on that side. Sorry. Now what we have, so now the spectral radius, it means that if the two, so remember the spectral radius is the sup, essentially, or the maximal radius of this set. So the spectral radius of this guy is equal to the spectral radius of that guy because of this relation. But so on this space, I know how to compute the spectral radius, okay? Because in this space, this space I'm in a space of functions. So let me write it this way, it's more symmetric. In this space, I'm in a space of function, okay? So what is the spectral radius? So this is the supremum sorry, let me think a moment. Yeah, on this side, actually, I have a nice, sorry, I have, yeah, this I forgot to say, otherwise you don't understand what I'm saying. And what is, so that's the interesting part, actually. On this side, so what is the spectrum here? So let's remind us what is the spectrum here. And this is the set of values for which lambda minus a hat is not invertible. And essentially, this means that phi has to send this to 0. And so on this side, one can argue that the set of the values of phi of a hat, of phi of a. So this is exactly, okay, let me, at a phi for any phi in sigma b. And this is exactly the set of values you can take, the multiplicative functionals can take on sigma b. And I wanted this because then when you have this relation, you can conclude, so the supremum here, it's really the norm. that I see what I want to say. Yeah, the norm of A hat. Yeah, okay, so because this set, so it's just the set of value essentially this function can take, and then this set of values, okay, then when you take the spectral radius, you take the supremum of this spectral value. So let me write, so this is the supremum of the absolute value, okay, so it's the supremum of that object according to the above, and then this is just the norm of this function, okay, so this is the norm of this object in the algebra. Okay. Let me see if this is, so I think this is the part of the point I still didn't explain somehow or justified. So let's see how it goes. So what is to be in the spectrum? Okay, so lambda belongs to that if lambda minus A is not invertible, sorry, here I mean this algebra, okay, is not invertible. But this somehow implies that, so this define, then from this you can get that one can prove that lambda minus A due to this condition. So this is, so actually from the discussion before, this is not invertible, but also this is not invertible. And then one can prove that essentially this guy is an ideal, maximal proper ideal. Okay, and therefore it corresponds to a linear functional. And if phi, by the reasoning above, the associated multiplicative functional, then, okay, so for any values lambda for which this is not invertible, you have a multiplicative linear functional. What is the, that is zero? So let me call this ideal I. Sorry, let me call this ideal I. Okay, so maybe, yeah, 0 on I. So what does it mean? In particular, in this ideal, you have the element lambda minus A. Okay, so let's see what I want to say. And lambda equal phi of A. Okay, so the idea is that for any, so this reasoning, this geometric reasoning tells you that for any value in the spectrum, there is a multiplicative linear functional which on A takes that value. Okay, so essentially, and you can go on the other direction. Okay, so you can prove also this equality quite easily. Okay, I don't want to give the detail, but somehow I think the idea, I explained the basic idea. From that, you can deduce that. Okay, so the spectral radius are equal and they correspond to the spectral radius on that algebra. Okay. Because here you can, so remember, and that's coherent with what we know, okay, because we know that this is the only relation we have between the norm and the spectral radius in general, is this relation. But on that side, you have equality because somehow the norm, you choose the right norm, okay, essentially, if you want, okay, the norm which works well with the algebraic structure of the Banach algebra. There is still not a C-star condition here. Okay, so that's how far you can go with Banach algebras. And now let's go to sister algebras, and then you have a theorem. And the theorem says if A is an abelian, a commutative, let's say. I use abelian and commutative, a commutative sister algebra. Then the map A, okay, then A is isomorphic to the space of continuous function or the Gelfand spectrum. Okay, and okay, this is the sister algebra. Okay, S sister algebra. Okay, where on the right we consider the involution. Okay, we consider the involution. Okay. Maybe I don't precise because somehow the idea is that I already proved to you that space of continuous function on a compact Hausdorff space is a sister algebra. Okay, with the involution with the involution given by the complex conjugate and the norm given by the supremum. Okay, okay, so any commutative sister algebra is isomorphic to a space of continuous function and on a compact Hausdorff space. Unital, okay? If it's not unital, then one has to do something else. But in our context, the unital ones are, so far they are the one interesting. If it's not unital, that this space, you will have to take function which vanish at infinity, essentially, and you require the space only to be locally compact. But okay, we don't worry for the moment to these things. And so let me specify what I mean is that I mean that they are isomorphic, okay? So they are not just isomorphic as algebra, but also the norm is preserved. And essentially the proof, okay, let not be formal. I will write more details in the note, but somehow what is the idea? Okay, so we proved, okay, so remember that for sister algebras, we have that if, so far we proved that if I is normal, then the norm of A, it's equal to the spectral radius of A. Okay, so this is what we proved before. Therefore, we have for normal elements, we have that the norm on the two sides coincide. Okay, so let me maybe be precise. Okay, so this is the spectral radius in A. Okay, but I think there is no risk of confusion. Okay, so you have, I'm trying to prove that it's isometric. Okay, so you have this property. Then what we have, let's see, so to be isomorphic, so already the Gelfand transform is homomorphism of algebras. Okay, so to be isomorphic, I need to at least to prove that the involution transform correctly, and that's actually less easy than said. So we have to check that the involution transform correctly. Okay, namely that. So what is that hat of A star is a. Okay, so this is what I want to check. Okay, on one side, the involution is the complex conjugation, so I need to check that. What does it mean that? Okay, it means that whenever you take the values on a multiplicative functional, Okay, so this function is the complex conjugate of this other function. Okay, so this means that, okay, for any multiplicative function. Okay, for any phi in sigma of A. And okay, so let's try to prove it. Okay, if A, assume A self-adjoint, then what we have, we can form. So if an element is self-adjoint, you can form, actually you can always form ut, okay, let me maybe call it ut. So this is the exponential of I at. Okay, so what does it mean? So this is, okay, this is one way to prove it. Okay, the idea is that I want to form the exponential of I at. I is the complex unit. Okay, so this is just it. So this is defined by the convergent series, as usual. And then you prove that this series is convergent for any t in the Banach algebra, okay? And check that it is unitary in A, okay? Remember, what does it mean unitary? Is that this guy, so the element is self-adjoint, okay? So A, when you take the star, you get the same thing. But of course, this change sign, so you get the opposite here. Okay, so here you will get like the product of this guy times the other guy, and then you reason by approximation, okay, by truncating the series and by algebraic operation, and then you realize that this is the identity. Okay, so this you can prove very easily and correspond to the properties of function, okay, by algebraic. Okay, by some analysis on the Banach algebra. Okay, we can form by convergent. And you can check this. Okay, so if it's unitary, okay, what does it mean to be that it's unitary? But it implies, sorry, it implies that okay, more, okay, let me say. What I want to say, so it implies, let me see what I want, yeah. It implies the following, so, so what is U star? So, okay, U, actually I don't need a star, maybe U minus T. Okay, maybe U minus T, you also check that it's U star and this. So what I want to say now, so what happens if you apply the multiplicative function? So I call phi a multiplicative functional. Okay, so what happens if you apply multiplicative functional? Well, you reason again with the series, okay, and then you get this. Okay, it's linear, and okay, you can justify that you can do by convergence. This is continuous, so it will, you can take the limit inside of the multiplicative functional, and it's continuous in the weak topology, but then it means also it's continuous with the strong topology, okay, because it's linear and bounded. It continues in a strong, actually, in the norm topology of U or on the Banach algebra. And then phi is multiplicative, okay, so here, see, here you can just take the power outside, and then you realize that this is, so is the exponential of it phi of A. Okay, so this is the multiplicative property, which tell you that remember what I want to prove. Okay, I want to prove this for self-adjoint element. So I'm looking at a self-adjoint A, then this would mean that phi is real. Okay, so essentially my goal, in order to prove that phi of A is real, I need just to prove that this is of size 1. But now we have, the norm of phi of ut, okay, so phi is continuous, is of norm 1, so yeah, you can say this is the norm of phi times the norm of ut, by definition of norm of 5 if you want. So this is equal to the norm of ut, but I told you that ut is unitary, and we are in a C-star algebra, so you check that unitary element have to be 1, okay? Have to have norm 1, since recall, okay? So the norm of ut squared by the C-star condition has to be equal to the norm of ut squared times ut, okay? And this is 1. This is the norm of 1, which is 1, okay? Therefore, we conclude what? We conclude that this is less than 1 for all t real, and this implies that phi of A is real, okay? Okay, so that's the first step. So if you have a self-adjoint and you have a multiplicative, then when you take the expectation of A on phi, you get a real. And that's coherent somehow. So you see, that start to be reasonable from the point of view of our interpretation, okay? A is unobservable. Phi is some particular state, okay? I have to show you that they are positive. They are normalized, surely. So phi of 1, it's 1, but it's not, we have yet to discuss positivity. But surely phi of A, it's real, so that's a good news for us. So what happens for a general element? So for a general A, so maybe you can imagine you write A as BF is C, with B and C, of course, self-adjoint. Then phi of A is phi of B plus phi of C, and phi of A star is equal to phi. So now you can compute A star. A star is just B minus AC. Then you have done. Okay, so this is exactly that. And that is exactly phi of A complex conjugate. Okay, so very easy to conclude. So we have proven that relation for general A. We have proven that the norm for self-adjoint element, so let me maybe put later because now I need it. So let me put here. Let me make a pause moment. So now we have to prove that this relation stays true for any element, okay? And in order to do so, you use, now use again the C-star condition to get, now I want to prove for any A in A, okay? So the C-star condition tells you that A squared, again, okay, is the norm of this element. Now this element sorry, got it wrong. This element is self-adjoint, okay? So observe that A star A is self-adjoint. Okay, so now I know for self-adjoint element I have that. Okay, so I know that this is equal to norm on the other side of the mirror, and that this norm is equal to the norm of the product. So let me do one step after the other. Okay, so now we are on the other side of the mirror. Okay, so now we have a product. I know that this is equal to the, so I denote like this. Think about this as a function. So this is really the norm. Okay, it's the sup norm. So this is, if you want, is the L infinity norm on that space. Okay, so let me write like this. So it reminds us what does it mean. It's the supremum, but the supremum is like the supremum of the product. But now this is the adjoint in the, this is the adjoint in the, in this star algebra. Okay, so means that I have another time the star condition here. So let's say by the sorry, by the star condition. So let me write in this way when I use the star condition is equal to that. So these are operation. Now I use again the star condition to say that this is equal to the norm of A squared in the star algebra. And okay, so we conclude, okay? So we conclude that the transform is an isomorphism. Okay, and okay, I have to check that it's 1-to-1. Okay, is 1-to-1. Since let me, okay, so and is 1-to-1, sorry, is 1-to-1. So because of the following, so let me see what I want to prove now. So I want to prove that if two elements are equal, yeah, okay, so since if, okay, if, okay, so to be 1-to-1 means that, that's the interesting part, okay, maybe, okay, think if two elements are, so if you get two elements, of course, linear functional, yeah, sorry, now I'm a bit confused. Okay, so, okay, if you take, let's try to prove one direction first. So if you take two elements and then you apply phi, and then you think that this gives the same function. So this is for all phi, then it means that phi of I minus b is 0 for all phi. Let's see, maybe it's trivial, but I don't see, so let's continue in this way. And then this implies that the norm of A minus B is 0, okay? Because, no, sorry, not yet. Yes, okay, because somehow this is the norm of this element in this side, okay? So you go on the other side, you get 0, okay? So they have to be the same, and then you reason on the other way. Okay, of course, this is in an isomorphism. Okay, and on the other way, you have similar reasoning. So okay, so this proves the theorem that I wanted to state. So this theorem. So as a consequence, let's conclude the proof of the theorem. By the way, which is so this is Gelfand-Naimark theorem is the characterization of commutative sister algebras. And again, okay, so the point there, we concluded essentially any commutative sister algebra is just is isomorphic to a space of function in an isometric way. let's take a consequence. So let's see the consequence of that fact. So we have maybe 10 minutes. So we have a nice point now. Sorry, I'm a bit lost. Yeah, I wanted to give, I want to give you exercise if you want. Try to think. Try to think, what does it mean? Okay, so take the space of n by n matrices. The space of diagonal. Okay. Prove that it is a sister algebra with the structure from inherited from the space of all matrices. It is the norm, is the operator norm. Okay, norm is the operator norm. Involution is the Hermitian conjugate. It's the adjoint, if you want. And what else? And product is the product of matrices. Okay. Okay, but they are diagonal. Okay, so don't get scared. Okay, so is and then try to think, try to work out the space, the structure. What is the space sigma of A? Okay. So the sister algebra. Okay, maybe prove that this is algebra. Okay, it's a sister algebra because it's generated by in the larger algebra. It's generated by the diagonal matrices. Okay, so it's a sister subalgebra of the space of all matrices. I didn't say that. Okay, I didn't say that the space of all matrices is a sister algebra, but I made the example of the bounded operator. So on a Hilbert space, if the Hilbert space is finite dimensional, then of course there's a space of matrices. Okay. So try to work out what is the spectrum of this algebra. Okay? That maybe could be interesting. It's a commutative, the commutative. And then I want to do another remark. So remark by the Gelfand-Naimer theorem. So we know something more now. Okay, we know that. Let me see what I want to say. Yeah, we now know that for any A in A, if A is commutative, we have, so remember what we have, okay? We have the rho A is equal to the norm of A. This is the property of sister algebras, but then I use, sorry, no, this I don't know yet. Wait a moment. Yeah, so I know that rho A is equal to the spectral radius on the Gelfand transform. This I know because I can compute the spectral radius and I can compare with the norm. So I know that this for any element is like that, okay, not only for the normal elements. Okay, that was the point for me. Okay, so this is equal for any element. But then I know that this is equal to A. This I proved before, okay, by this, okay, which extend what we knew before only for normal elements. Okay, so this is what I told you. Okay, so okay, it requires this more complex line of reasoning. In particular, the non-trivial equality is this one, which require the full knowledge of the structure of the multiplicative functionals. Okay, and this involves the structure of the ideal. Okay, so this equality, yeah. So somehow these are the qualities we proved today, and so this completes somehow the picture. And you see, for any okay, yeah. So so this complete this picture somehow in that case. Good. Okay, so I wanted to say that. But then, of course, this is only true only if A is commutative. Okay, then you can say then any element is normal. Yeah, actually, you're right. So maybe this is not very interesting. Yeah, so sorry. So this let me say, with which coincide with what we knew before only for normal elements. Okay, but okay, the observation. So okay, let me restate this observation in that way. Sorry. Yeah, somehow normal in a okay. That's okay. That helped me. That help me start what I want to say now. So if you take a normal element, then somehow it generates a commutative sister algebra. So in a general setting, of course, the structure theory we made, it's valid for commutative algebras, but somehow for a general sister algebra, you can apply it to sub algebras which are commutative there. Okay, so the GN theorem give us a functional calculus on normal elements, a continuous functional calculus, a normal element of a general sister algebra. How so? Indeed, observe that for any so now you take a generic element, the algebra, so the sister algebra, so let's write in this way, generated by A, so the sister algebra. Meaning that you consider also the involution and the unit, okay, is commutative for any normal A, otherwise you don't know, actually it's false. It's commutative, okay, then you can define the Gelfand transform, okay, then there is an isomorphism sister algebras into, okay, so let's write this way. So this sister algebra is isomorphic to the sister algebra on the spectrum, okay, of this sister algebra. Okay, so it's a bit confusing. Okay, yeah, let's write like this, but with the understanding that I always consider also the involution, okay, in the algebra of complex functions. Okay, and so, but now what is this set? Okay, and now, so I leave you as exercise. Is not difficult to show that actually what is this space? So this space, it's really the spectrum of A as a subset of C. Okay, so that's the interest. So when you take a single element and you look at the Gelfand spectrum of the sister algebra, you get the spectrum of the element. Okay, that's why you use this notation. Okay, this, remember, somehow the same symbol we use for the spectrum. So this is really, okay, this is really the sigma algebra on this of continuous function on the spectrum of A. Since, okay, since, if you want. Therefore, so if you give me function f, okay, from sigma A to C, continuous function, then this defines, because I have this homomorphism, okay, so this defines an element f of A of an element in this sister algebra, okay, by the relation that the Gelfand transform of this element has to be this function, okay? Okay, that's the relation, okay? So the map is one-to-one, so to any continuous function, you get such an element, and then you call it f of A, okay? And it has all the, and essentially you can do, moreover, okay, you can prove things like f of g of A, it's equal to the composition of f and g of A, and etc. Okay, so that f of A is self-adjoint if f is real function, and etc. Okay, and many other properties like this. So I stop here for today. So we introduced a lot, and essentially now we are in position to discuss. So next week we will discuss positivity in sister algebras. Okay, so I need a notion of positivity here when an element, okay, when I say an element is positive. Remember, in our somehow modelization of an observable, I at some point require that if the observable is positive, then the value on the states, the measurement of this observable on the states are positive. So I have to understand the notion of positivity in the context of sister algebras and the notion of state of positive linear functional, related notion of positive linear function, okay? And positive functions. In that way, I will be able to understand the notion of states when put into the context of sister algebras and how the state look like. Okay, and after that, so I think this will require another lecture, and then we start to discuss representation theory. Then we start to discuss need of non-commutativity, and this will involve Heisenberg. Heisenberg indetermination, principle. So we will motivate, at least intuitively, that somehow it's not reasonable to request that all measurement can be performed with arbitrary high accuracy. Then this will imply that somehow a way to implement this requirement is to require non-commutativity of the algebra. And then we will look to the representation theory for non-commutative sister algebras. Okay, so far so the theory we discussed today, so the theory is the representation theory of commutative algebra, and essentially it completely and fully satisfies the answer of ever structure theory for commutative sister algebras, okay, because essentially tell you commutative system algebra is just an algebra of functions, and you understand functions very well. And non-commutative algebras, I motivated the fact that this approach does not work very well. Somehow you need a larger representation space. So space of function, complex values function is not large enough. And why we want non-commutativity? Because somehow this is physically justified. Okay, so this will then allows us to introduce the setting of classical setting of quantum mechanics, that is Hilbert space. And then we discuss what is the freedom or representation on Hilbert space, Hilbert spaces. And yeah, so we discussed some topic about representation theory. In particular, we will see that essentially when you look at finite dimensional quantum system, there is only one representation that cares, and this is the Schrodinger representation. I mean, all the representations are equivalent. Sorry, let me say it like this. All the representations are equivalent, so you just study the most convenient. This will allow us to introduce the Schrodinger representation, which is maybe the one you know if you know some course of elementary quantum mechanics. And then we start to discuss how to perform the weak rotation to get a probabilistic system out of that. And so for today, I stop here. Thank you for your attention. Are there any questions? I don't, so let me stop maybe recording.